I was an undergraduate at Trinity College Dublin, and in fact I was in the same year as Martina. Where's Martina? She's here somewhere. And a big thank you to Martina, by the way, because she also invited me to come to this talk tomorrow, by a strange coincidence. And Martina did genetics, and I did biochemistry. We never met, strangely, back then. But as part of our degree program, we do a final year research dissertation. And I did biochemistry. And in the Department of Biochemistry in Trinity, it was mainly enzymology, and I hated enzymes with a passion, which is very strange doing a biochemistry degree. And you could pick a project from a list, and one project stood out for me, and it was called Prostaglandins in Crohn's disease. And that got my attention because I said, what are these prostaglandins? And as you all know, I hope they're these lipids that cause inflammation. And Bruce told us about Crohn's, still a big problem. I did that project in 1985, and it began my interest in inflammation. And prostaglandins were really hot at that time. They were the tolls of their day. There was incandescence around them. Everybody worked on prostaglandins. They were driving inflammation in all these diseases. So for my PhD, I went to London. I went to this place. This is one of the meccas of prostaglandin research. The Royal College of Surgeons in London. And in that department in pharmacology, a guy called John Vane had won the Nobel Prize. He was my first Nobel Prize person I met back then. And he discovered how aspirin works. And I went there to study prostaglandins because aspirin works by blocking prostaglandins. And a little anecdote for all you young students. There's me there. Before the ravages of age took over. That's 1985. Look, at rheumatoid arthritis, even then I was working on that. And I was there about 3 months as a postgrad. I couldn't speak English then. The Irish could only speak the Irish language, as you know. The English had tried to destroy it, but we had survived. And I was there about 3 months, and Vane came to give a seminar. And he arrived, he was in the car park, and we all saw him come in, and he came up and he gave this seminar. And about halfway through, I spotted an inconsistency in his talk. He said something that didn't quite gel for me. Now, at the end of his talk, the chairman went, any questions? And would you believe a timid first-year graduate student that rose my hand tentatively? I was sitting at lunch, actually. How many years training does it take to get someone to ask a question at a seminar? Probably 8 years. Yeah, most people are too frightened. But I put my hand up and I asked him this question, and he said, that's a very good question, I don't know the answer. He said, come up and see me afterwards. And I went up afterwards, and we had a chat, and he said, yeah, great question, I'll write to you, there was the days for email, and he sent me a letter with the answer. That single conversation, let this be a warning to our current 2 Nobelists, convinced me science was the business for me. That a Paddy off the boat from Ireland, who could hardly speak English, but challenge a Nobel laureate and catch him out almost. And he was saying, that's a good question. I said, this is the meritocracy. It really kind of energised me in that situation. That was great. And he was a big influence as a result, and there he is. And again, he won the Nobel Prize, as I say, for showing that aspirin works and similar anti-inflammatories. Aspirin works by blocking prostaglandins. And he showed prostaglandins were the key programming factors. Now, he had published a paper in Nature. He won the Nobel Prize on that single paper in 1971, inhibition of prostaglandin synthesis as a mechanism of action for aspirin, because it was a big unknown area. Now, my PhD project was all about prostaglandins, and at that time, this was the pathway for prostaglandins. There was arachidonic acid that was made, and you get an enzyme called cyclooxygenase that makes PGE2. Aspirin worked by blocking that enzyme, and that not much was known about the control of that pathway. Calcium was known to be an important signal, but 2 brand new fangled mediators of inflammation had been found in the mid-80s, and Bruce discovered one of them. One was called TNF, the other IL-1. These are cytokines made by macrophages during inflammation, and they were known to be very powerful inducers of prostaglandins. And my project was figure out how they work. How would IL-1 increase prostaglandins? And my very first project was IL-1, very powerful. What's its mechanism? These newfangled things called cytokines. And I published a paper in 1987 in Feb's Letters showing that IL-1 was inducing cyclooxygenase. Now, this was all done indirectly. We didn't clone the gene, but it was evidence that the COX enzyme was somehow being induced by IL-1, and I got a Feb's Letter paper out of that. And this turned out to be correct, amazingly. And other people then went on to clone the gene, and the people who are pharmacologists will know there are 2 types of COXes, good COX and bad COX. The good COX is in your stomach and protects you. The prostaglandins are cytoprotective. The bad one's inflammatory and causes all this inflammation through prostaglandins. And why this was important was aspirin blocks both, and so does ibuprofen. And of course, that's why it causes ulcers, because it stops the good COX and the bad COX. This led to the industry developing COX-2 specific inhibitors. And Celebrex and Vioxx came along, and they were much better now because they spared the stomach and there were no ulcers, but they were anti-inflammatory. Of course, troublingly, they got withdrawn, and that was another Irishman, Gareth Fitzgerald, spotted that Vioxx in particular had problems in the heart. It causes heart attacks, and they get withdrawn. But when they were launched, they were huge drug deals because they replaced all the other anti-inflammatory agents. And my project was part of this, because we showed induction of this special COX, which became known as COX-2. And then I wondered how this pathway would work, and in 1988, this was our version of IL-1 signaling. We thought the receptor, which hadn't been really cloned then, went into the nucleus somehow, possibly, and turned on the gene for COX. And I got this from my PhD thesis. I gave this talk about 3 months ago about my PhD, and I had to use, remember we used to use these diazo group slides, Bruce? I had to turn one of those into a PowerPoint. And that was our knowledge of IL-1 signaling. And I was relentless. I wanted to know, how does IL-1 work? Can we understand this powerful cytokine, which is prodigiously pro-inflammatory? And then my next move was to go to Cambridge in the UK, and this, Murray, was my scientific father, actually. He was my postdoc mentor, Jerry Saclavada. He had discovered, in many ways, that IL-1 and TNF are key for arthritis. He was one of the key pioneers. And secondly, he was characterizing the receptor. And I figured I'd go to his lab, because if we can study the receptor, we might know how the thing works. And in the 90s, of course, this was our model for rheumatoid, like dominoes, and the final domino falls over being rheumatoid arthritis. IL-1 and TNF were here, and they were driving this process, and of course that gave rise to drugs to block these cytokines. And anti-TNF came along as a key way to treat arthritis, because, in other words, TNF was proven to be a key domino, and that's earned billions for drug companies. I'm sure Bruce is amazed by that fact as well, having discovered TNF. And that still is a mainstay now for rheumatoid. But of course, the question was what drives it. I'll come back to that in a minute. But my question was, how does IL-1 work? How does it knock over these dominoes? And we just look at the receptor. This is from my postdoc. There are 2 types of receptor, the type 1 receptor and the type 2 receptor. And that was all very well, and I'm kind of chundering along. We were reviewing in 1990 about IL-1 signaling that appeared in Trends in Immunology Today, as it was called. And it was very disputed at the time. There was evidence that cyclic AMP was a key signal for IL-1. And we wrote a review saying, no, it's not cyclic AMP, that's nonsense. We said it was NF kappa B and P38 were the key signals, and this was the real fight at the time. And I was happy with this review. It was one of the early reviews on IL-1 signaling. And this was our view of signaling in 1991. We knew NF kappa B was in the pathway. IL-1 somehow activated it, and the inhibitor fell off, and it was all a bit simplistic, really. And then the annus mirabilis arrived. And I met a guy in Cambridge called Nick Gay. Now Jules was mentioned him, and he's a really important figure in the history, as I'm sure Jules and Bruce would agree. And he was a postdoc in Cambridge, and I met him, and he used to have many a collaboration with Arthur Guinness, who I actually thought I put him as an author on some of my papers. He was so influential. And Nick had seen my review, and in the Drosophila world at that time, Jules may remember this, there was evidence of toll driving cyclic AMP strangely, which nobody quite believed. So there's kind of a parallel world going on with toll and IL-1, and that got Nick thinking. And Nick amazingly shows that the IL-1 receptor is homologous to toll. And he had a letter in Nature in 1991, and this was quite advanced. Bioinformatics was early then, and used to draw graphs, and there'd be one amino acid sequence this way, one that way, and dots on the diagonal meant identity. So whole stretches of toll and IL-1 were identical, and it was the cytosolic domain, as you has mentioned. And I saw that paper, and that was the key paper for me, because at that time, the IL-1 receptor was unique in the database. It didn't have a tyrosine kinase domain, it wasn't a GPCR, and we're all going, what the hell is this toll thing? And what's it doing with this domain that's homologous to the IL-1 receptor? But extremely importantly as well, in 1994, and this is another key paper, Barbara Baker's paper comes out and said that we all saw as well. And she says, in Berkeley obviously, she says there's another protein called N protein. And this protein N, again, it looks like the IL-1 receptor and toll. That was our big cell there. Dinesh is here. I used a co-author on that. And that really got our imagination. Here we got a plant protein now with the same domain. And in 1994, later that year, John Sims, who had cloned the IL-1 receptor, gave the first account of the family. And here's this black thing is the third domain, which Barbara named, by the way. And there's toll, 18-wheeler, and there's N protein. And this one here, look at this. This is the first human toll to be reported. John Sims spotted this by bioinformatics. It's RST786. Turns out to be toll 1, and that's 94. So they were spotting these already in many ways. And then, of course, Hughes' paper comes out, the Nobel Prize, I call it. I mean, imagine winning a Nobel Prize because of a cover of a magazine. It's a great achievement. And I want to mention this show for you especially. This is basic research at its finest, right? He wins the Nobel Prize for Medicine, never having gone near a human being. And Sarkozy, our hero, said this last year. Look at this. He said, without basic research, there can be no applications. After all, electricity and electric light bulb were not invented by incremental improvements in the candle. Right? And that's a very telling statement. And Joule continues that tradition. Now, another thing to point out, this is for Murray. the importance of IL-1, if you've got an IL-1-centric view of the world like I do, IL-1 was the foundation for the two big breakthroughs in immunology, because first of all, the enzyme that cleaves IL-1 is called ICE. That was the founder caspase. And meanwhile, in the worm, they find SED3, and that's a caspase as well. That provokes the apoptosis revolution. Equally, the IL-1 receptor in toll, and the third domain provokes the innate immune revolution. So without the work on IL-1, neither of these would have happened, is my firm opinion. I then do a review in 1998, because at this stage 5 tolls have been described, called TLRs, no ligand yet, and yet more plant proteins. I mean, this amazed me, even though I was writing a review featuring plant proteins, having the third domain, and I make the point this is conserved for evolution and all the rest of it. But then the very important step happens with Bruce and Alex Poltorak. And in fact, in Jerusalem at a meeting, I met Alexander, and he told us all, told 4 is the missing receptor. And as Bruce has mentioned, the difference between this mouse and this mouse is a single amino acid. So there's a histidine in TOL4 in the HEGA that makes it unresponsive. It's a proline in the HEN. So Bruce won the Nobel Prize for a single amino acid difference, which is very impressive. Let's face it. Here we have it. And we know about the Nobel and all the rest of it. Now, this is the first Nobel for pure innate immunity since Meshnikov, as you all will agree. Meshnikov in 1908. And he finds phagocytes, and he talks about, look at this, animal organisms are very complex, so we choose lower animals. There's a lot of parallels here. And very importantly, guess who mentions Meshnikov? Our great hero, James Joyce. This is Marilyn Monroe, strangely reading Ulysses. Look at that. And I was asked to give a talk at a Ulysses celebration about 3 years ago, and Joyce was a very learned man. And you can search Ulysses now online, and I searched for infection, and guess what I came across, which I hadn't seen before. This is from Ulysses. Kitty says, and Mary Shortall that was with the pox, this was set in a brothel, this scene, she got from Jimmy Pigeon. And look what Dave says, and to such delights as Mechnikov inoculated anthropoides. So Joyce quotes Mechnikov in Ulysses. And I'm going to have to write a book now and quote Jules and Bruce. You see, I'm putting a marker down. I'm going to be Ulysses next. But Mechnikov is very famous, and that's how Joyce mentions him. So, and then of course, this was the whole third domain family. We had this already with the IL-1 receptor, so family, the tolls themselves. Very important, the adapters, and I spent much of my life working on these. These plug in, you get tertiary interactions to launch the signaling path. There's 5 adapters, and they work in various ways for these receptors to signal. And as we've had already, wonderful conservation. There's the fly, and there's the human. MyD88s in both, the IRACs are there, the NF-kappa B system. So as we've heard several times, strong conservation through evolution is the key point here. And very importantly in plants, and this wonderful review, and I read this as well, Murray, this was fantastic when I read this, that Bruce and Pam wrote last year. It's a pretty fantastic account of this homology. And I advise you all to read it because it's very well written and conveys the whole business. Now, by this stage then, we were all happy with tolls, and I'm looking to be working on IL-1. Hadn't published much apart from a couple of reviews. And then in the year 2000, we published this paper in PNAS, and we found 2 viral proteins that block toll. And one was called A46, or the A52, they're in vaccinia, and they block toll and IL-1. And that was the first link between viruses and tolls. This is before they figured out that certain tolls are antiviral. And to my delight, Charlie Janeway wrote a commentary on this, viral interference with IL-1 and toll signaling, and that was great. And he mentions this because he says, look, if viruses go to the trouble of targeting tolls must be very important. And they must be very important for antiviral host defense. And of course, just to emphasize Charlie's importance to immunologists largely, inflammation people don't really recognize him in the same way as immunologists do. He wrote a very important review called Approaching the Asymptote, and in that he says, look, he says, if us immunologists only study adaptive, not to be up on the asymptote, we won't go any further. We need to study innate as well. And really what he was saying was, you immunologists are stupid. You've just focused on the antigen from the microbe. He said there's also these things called PAMPs. And these receptors then recognize these PAMPs. And it turns out to be that the receptors, like tolls, drive the cytokines, and that was very important. Their function is to drive cytokines and promote antigen presentation. So the 2 bits of the pathogen is what you need to get a full immune response. And Janeway postulated on that, and it kind of predicted this in many ways. And then the 2 main I'm going to talk about, tolls and inflammasomes, are the 2 main ones that I'm going to be mentioning mainly here. And because my work was mainly about how do tolls work, being a biochemist, and we find these adapters. We discover 2 of these, and we figure out how they signal. And here's MyD88, maltrif, and tram, and they plug into tolls and launch the signaling pathway in various ways. That's the complex version of toll signaling. Here's the simple version. We work on one of these proteins. You are up here somewhere. Pretty complex signaling, obviously. Great triumph, by the way. I mean, there's wonderful structures now. This was solved by Hao Wu last year. This is the midosome. You get a stoichiometry of 14 proteins assembling with 6 MyD88s, 4 IRAC1s and 4 IRAC4s zip up into this big structure, and that's what launches the whole thing. There they are as a cross-section, and you get kind of a little movie where they all assemble. And what I've shown you there is the launching of innate immunity. So all the tolls and all the IL-1 receptors, and I suspect in plants as well, you assemble this highly stoichiometric 14 mark to launch signaling pathways. And that's a real triumph, I think, of basic biology and structural work. Now, moving on to my second topic, is any of this useful? And of course, if it is going to be useful, it'll be useful in inflammation. I suspect this doesn't happen much in California. This is chilblains. Did you ever get those, Marty? No. Inflammation, a really important process. And in fact, it's got very trendy. And yet another Nobel Prize winner, who's a personal friend of mine, David Baltimore, I met him last year. He discovered NF-kappa B among many things. At a conference last year in Cincinnati, he said this, and I made a note of it. He said, cancer, atherosclerosis, metabolic disease, autoimmunity are all secondary to chronic inflammation. This places inflammation at the heart of modern medicine. So in other words, inflammation is key to most pathologies. That's the first statement of fact. Why would this be? It seems a bit strange. Well, I think this is one way to think of it. Inflammation actually is supposed to do you good. It's supposed to respond to an injury and then restore the balance. And what's happening is disease could be defined as a displacement from homeostasis. Let's think of homeostasis. And the job of inflammation is to sense that first of all and then restore it. That's what the inflammatory process does. And when it goes wrong, you get disease. So this concept of homeostasis emerged. And guess what? The toll-like receptors and the inflammasomes are prototypical sensors of this imbalance. And secondly, they drive pathways to restore the balance back, and that's why they're so important. And the word homeostasis is interesting. My labs give me a gift every Christmas. They gave me this book last Christmas called F in Exams, and it's the worst collection of exam questions. Those of you who teach, you know when a student is desperate to write an answer down, and they write any old rubbish to hope to get a few marks. There's a couple of great ones I'd rather say. I just spotted this recently. Explain the concept of homeostasis, and some student wrote, it's when you stay at home all day and don't go out. So I would give that full marks. And especially for Dr. Hoffman, in the Hawaiian Islands there are around 500 different species of fruit fly. Give a reason for this. There are approximately 500 varieties of fruit. I could be here all day with this. But moving swiftly on. So, the concept to get across, the take home, tolls sense this deviation. They sense the deviation in homeostasis and drive inflammation to restore it. That's the concept we're talking about. 3 or 4 quick examples that I love from the literature. About a year and a half ago, a paper in Nature Immunology, contact dermatitis, a skin disease. It turns out that mice, very hard to get a model for this in mice. You need to give a very strong adjuvant, right? And they use nickel is the model here, right? So in mouse, it's very hard to drive this response. In humans, nickel alone suffices. People are allergic to nickel, as you know. These clever people spotted in TOL4 there are 2 histidines that coordinate the nickel and cross-link the TOL4 molecules and drive the inflammation in skin. Mice do not have histidines at that position. They humanized that mouse for those 2 histidines, and guess what? The mice got contact dermatitis. So there we have one example where TOL4 is key, simply because nickel is being sensed as a sort of a toxin of sorts, and it's cross-linking TOL4 to drive the pathway. So therefore TOL4 could be good there. Second example here. Very interesting this. It turns out that toll ligands are very useful adjuvants for vaccines, and they're being developed in various ways. A second example though is toll7, which senses nucleic acids. If you inhale toll7 into your airways, you desensitize the airways to allergens. Right? And that's the various reasons why that might be. And this was in the Daily Mail jab for hay fever. This is a company developing a toll7 agonist, which will actually desensitize you to allergens, and there could be an application there for activating tolls. The third example is rheumatoid. Back to rheumatoid again. There's lots of evidence now for tolls being dysregulated here. Here's a mouse model of rheumatoid. It's a spontaneous model. The joint narrows, all this debris. You can treat those mice with a TOL4 antagonist and reverse that pathology. And there's various ideas as to what might be activating TOL4. Here's a whole host of endogenous ligands, and we discussed this earlier. This is a steroid situation. And there's evidence for all of these factors going through TOL4. It's most unlikely, I guess. But what they all have in common is they're either necrotic cell products or the connective tissue breakdown products. So perhaps if you damage connective tissue, you cause an imbalance in homeostasis because the connective tissue is broken, and tolls sense that somehow. Now whether it's tolls sensing them directly, I have a hunch that these are picking up commensal LPS action, and delivering that. That's one option possibly here to discuss. But TOL4 has a role driving TNF and IL-6, of course, very importantly. And our company, Opsona, which I'm going to mention actually, because we're trying to develop drugs here, we have a TOL2 inhibitor. That's an antibody, and we put that inhibitor into rheumatoid. This is human rheumatoid arthritis. You can culture biopsies from rheumatoid patients. Those biopsies release loads of TNF, and look, our antibody can block TNF production, or IL-6, in this ex vivo system, suggesting in this system that TOL2 is driving these cytokines, and blocking TOL2 then would stop the TNF. And as I mentioned, blocking TNF is a multi-billion-dollar industry in rheumatoid. Perhaps the TOLs, therefore, but I have my domino effect here again. Maybe TOLs are very early then, and they're driving the cytokines then that drive on the inflammation, placing these receptors very early in the cascade of events. And that's a very interesting idea, we think. Now, let me talk about our own drug, though, for a minute. So I specifically want to talk about this to illustrate how you can do interesting commercial work. So about 7 years ago now, I was approached by an Australian guy, cold call on my office one day, and he said, "I'd like to form a company around your research." And at that time, we had patents on those two viral proteins, because they could have been anti-inflammatory. And we also had a patent to do with TOL4 signaling. And he said, I can form a company around that. We called the company Opsona, and our lead product is a fully human anti-TOL2 antibody called OPN305, and it blocks TOL2 specifically. All these diseases, you'll see evidence for TOL2, autoimmunity, acne, interestingly, atherosclerosis, diabetes, and infectious diseases, and cancer as well, metastases, but it will be driven by TOL2. But the one we homed in on, strangely, was ischemia reperfusion injury. That was the one that looked most interesting to us. And our antibody very nicely neutralizes PAM-CIS driving TNF, and here we see a dose response to it as an isotype control, beautiful inhibitor of TOL2-induced TNF. And we looked at ischemia reperfusion, which is a very strange thing to look at for me, because I have no interest in this at all. And we looked at two tissues here, the heart and the kidney. Now, why did we do this? Well, I was stimulated by this single paper, a paper that came out in JCI by a Dutch group, led by a guy called Floorkamp and Leemans, where for some reason they were kidney doctors. And they noticed that in the ischemic kidney, now what ischemia is, by the way, is a cut-off of the blood supply. That's all it is. If you cut off the blood supply, ischemia happens. It means oxygen starvation. If you cut the blood supply off in the kidney becomes ischemic, or the heart, or the brain. It's only when you release the blood and cause reperfusion that you cause the inflammation. It's called ischemia reperfusion. And the tissue floods with neutrophils, and the tissue gets destroyed. This happens in a heart attack. It happens in kidney transplant, it's well known. And these guys spot a key role for TOL2 in sensing that imbalance and then driving the inflammation. And they had a TOL2 knockout. This is ischemia here in the kidney in the wild type. TOL2 knockouts a lot less. They put an antisense to TOL2, and here we see again ischemia. This is granulocyte infiltration actually into the reperfused tissue. An antisense to TOL2 to block that. Michael, that's interesting. Let's look at ischemia reperfusion injury. And we did a pilot study with knockout mice. This is a heart model where you cut off the coronary artery for 30 minutes and then reperfuse, and you cause a heart attack and infarct. And this is all dead tissue here in the wild type heart. Here's TOL2 knockout, a lot less tissue injury in the TOL2 knockout. And then we tried our antibody. And as I said, if you reperfuse, you get a massive pulse of cytokines in the reperfused tissue, loads of TNF floods out, loads of GM-CSF, and look, our antibody can completely neutralize all the production. And we give our antibody just before you reperfuse. Secondly, neutrophil infiltration. Neutrophils rush in here, 2 different time points. Again, our antibody very effectively stops the neutrophils. It also stops macrophages to a lesser extent, but it's still significant. So it stops all the inflammation. Very importantly, then, if you measure the heart, the infarct size, like the dead heart tissue. This is the IG-treated control mice. Here's our antibody treated. You get about a halving of the injury in the heart if you give our antibody before you reperfuse. Just as good as TOL2 knockouts in many ways. And then we also have scarring, isn't it? The tissue becomes very scarred. And look at this. This is 28 days later. Here we see the untreated. Here we have our antibody limiting the scarring in that tissue. And then if you're a cardiologist, and there may be some of you here, you've got to measure heart function. You measure systolic volume, for instance. The systolic volume in the heart is the amount of blood the heart's pumping. It goes up in the injured heart because the heart can't pump as well. So the blood begins to gather, and that's an injured heart. This is the diastolic volume. And look, our treated animals, 28 days later, this is a normalized heart here. It's pumping normally for those two volumes. So again, rather surprisingly, we've evidence that TOL2 in ischemia reperfusion is causing all this injury. The pig is the model of choice. We've just done our pig trial, and pigs are much more like humans. Some pigs more, some humans more than others, he said. And yet again in the pig, here's the infarct science here. Here's our dose response to our antibody. limiting the infarct there. You can measure troponins as a measure of heart injury. And again, the troponins go up in the injured heart, and again, our antibody lowers the troponin, and it correlates perfectly with the lowering of the infarct size. So we've got very good evidence then that Toll-2 is driving the inflammation that kills the heart in the case of ischemic perfusion. Now, you wouldn't go after this in a clinical trial because it's quite hard to do trials in the heart. Instead, we've turned to the kidney, and it's very similar. The ischemic kidney, it's all about Toll-2. And we just published this paper to confirm this. Here we see a kidney transplant, and this here is renal failure. This is a marker here called bun in the injured kidney. And here again is our antibody. Very nicely limiting injury there. You can clearly see that. Here's the actual tubules. These are quite damaged tubules. Again, with our Toll-2 antibodies are protected. So again, in the kidney then, we've got Toll-2 protecting. And all of this provokes us into a clinical trial. And in July of last year, we were the first company to block Toll-2 in humans with our antibody in a phase 1 trial. Did a healthy volunteer study, 31 in the active group, 14 in the placebo. We got dose-dependent blockade of Toll-2. We could show that in peripheral blood. We could challenge the blood from the people with Toll-2 ligands to show Toll-2 was blocked. Thankfully, no adverse events. And that was nice. The first company to block Toll-2, because it could be a safety issue here. Nobody's blocked Toll-2 before in humans. And now our phase 2 will begin in June in kidney transplant. We've got 10 transplant centres to see if our antibody can help in kidney transplant. Now you might think kidney transplant isn't a clinical problem. It remains a major problem. And of course, we're the first people to block an innate pathway in transplant. Most of the drugs are immunosuppressants. And in about a year or so, we'll have the results of that trial. And given our data in the pig, which is a real model for this, we're optimistic we'll have a way to help kidney transplantation. And that may be the first place where we'll see a toll inhibitor working. Now, the last bit I want to talk about then is IL-1. So, you could look at tolls in lots of diseases. Why do we go after ischemia? Simply because we have good data to support that. Other companies are developing Toll-7 antagonists for lupus, for example. There's companies developing Toll-4 inhibitors for various indications. There was a big trial done on gram-negative sepsis with a Toll-4 inhibitor which failed, sadly, probably because it was too late. So there's activity around these different tolls, and we're out there with Toll-2, we're talking about Toll-2 and ischemia. Of course, we might go into rheumatoid, we might go into lupus, where there's evidence for Toll-2, but our first area is going to be kidney ischemia injury. Now, the last thing I want to talk about then is similar in some ways. It's this resurgence of interest in IL-1. And it's back to where I began in many ways. And these are these inflammasomes. Now, as I said already, there are a second family of receptors. The tolls came first as the first PROs. Inflammasomes came along quite quickly soon after. People like Jörg Chopp, who sadly passed away last year, a key pioneer here. And these turn out to be very similar, and they've all got leucine-rich repeats, of course, like all the family would. And what they do is they drive IL-1, so that they're specifically able to drive IL-1. They also drive IL-18, and they activate an enzyme called caspase 1. And as I mentioned already, that was the founder caspase, and that processes the pro form of IL-1 to make the mature form. And these inflammasomes sense various things. There's one called AIM2 that senses DNA, NLRC4 senses flagellin, and that's quite like a plant LRO-containing protein. NLRP1 will sense lethal toxin from anthrax, for example. But this one is the one of interest to us now, 3. That will sense many factors, actually, and then drive again the inflammasome, and ASC is a key protein that comes. So 4 inflammasomes, great interest being generated because of IL-1. And why is NALT3 especially interesting? Well, there's a genetic disease, there's several types of diseases actually, where people have mutations in NALT3, and they all get horrible inflammatory disease. They get fevers because of IL-1, they get amyloidosis in their kidneys, and all these diseases here basically are NALT3 mutations. And that was a very important discovery, really. If you mutate NALT3, you can drive IL-1 production cause disease. But probably as important is, it turns out, what NALT3 does is it senses particles. So it senses uric acid, whatever that is on the slide, over here, uric acid. It senses cholesterol crystals. It senses beta amyloid. Any particulate will drive IL-1, and that's been known for years, like phagocytosis drives IL-1. And it turns out NALT3 is sensing all these particles. It does it in infection by sensing viruses or bacteria. But it also senses these noxious substances and then drives IL-1. And that's really provoked a lot of interest in different areas. And you still need the tolls because they drive what's called signal 1, NF-kappa B, for the pro form of IL-1 gets made. And then the inflammasome gets kicked off by all these particles to activate caspase 1 to mature the IL-1 into its final form, and then it gets secreted. And NF-kappa B is key for this. So you need the tolls and the inflammasomes then to drive IL-1. This has given rise to a big interest in IL-1 again clinically, and there were 3 inhibitors approved. There's the IL-1 receptor antagonist. Canakinumab is an antibody. Now there's a great name for an antibody, canakinumab. It sounds like Can I Kill You Man? I had pulled up art just recently when they weren't too happy. IL-1 trap, these are all in trials. Where would you use them? Well, these strange genetic abnormalities are called cryopyronopathies. There's gout, diabetes, juvenile arthritis, Behçet's, ankylosing spondylitis. All of these probably have a dysfunctional NALM3 and making IL-1 an attractive target from that NALM3 pathway then. And look at this here. All medicine will one day be like this. This is Muckle-Wells syndrome, very rare. It's a mutation in NALM3 in patients. It drives IL-1. This was a death sentence with this, so people lived and then died in their 20s. They have a systemic inflammatory response. This is a patient with a skin rash, there's iritis in the eye. A single injection of anti-IL-1, 24 hours later, all the inflammation's gone away. Look at that. And here's inflammatory markers in blood. That's is that CRP? There's SAA, an acute phase reactant, and that's CRP. Normalised. Look at that. And it normalised for nearly several weeks here. And maybe one day all diseases will happen. This is a single genetic mutation driving IL-1. It's cured effectively by blocking IL-1. So there's big hope now. And the one little quick story I would say is with type 2 diabetes. There's very good evidence for IL-1 beta driving type 2 diabetes. And we wondered what's driving IL-1. This isn't an infectious disease. What would be the driver of IL-1 in type 2 diabetes? And we turned to an amyloid type protein called IAPP, which gets laid down in the pancreas of type 2 diabetics. A fantastic NALM3 activator. And here is some of our evidence. There's IAPP driving IL-1. There's uric acid. Here's NALM3 knockout. It's completely spared of that, so it's NALM3 dependent. And then very nicely, we've got a mouse model. It turns out rodent IAPP does not form amyloid, and they don't get type 2 diabetes. You can make a transgenic mouse where you put the human IAPP into the mouse, and those mice develop type 2 diabetes, and they deposit. All this amyloid gets deposited, and lots of IL-1 gets made. And it co-localizes them with the amyloid here very nicely. And it's not the beta cells. The beta cells begin to die off here. So the red is insulin, and they're all dying off. And it doesn't co-localize with the beta cells. It's all macrophages are gone in. And we showed this by staining actually. We use a macrophage thing called MAMA2, which is green, these dots, red over here for the macrophage marker, green for IL-1 co-localization. So it's macrophages going in to take up this IAPP. And this allows us to come up with a model for pathogenesis. And I think it's very important that the discovery of these receptors allows us now to get closer to having a really good account of why these diseases happen in the first place. And in the case of type 2 diabetes, this would be our hypothesis. There were several papers last year showing lipids in the fat tissue. Palmitate and ceramides will activate NALM3, driving IL-1. Now what does IL-1 do? It causes insulin resistance, and that's been known for years. And what happens next is the pancreas then starts to make more insulin in response. And IAPP is a natural hormone that's made with the insulin, but it has this misfortune of forming amyloid. So all the insulin is getting made, IAPP is made as well. It forms amyloid, macrophages go in, sense the IAPP with NALM3, drive more IL-1, and then we get lots of IL-1 being made, and it kills beta cells and causes further resistant insulin. So there's no infection at all here. This is the metabolic imbalance that's driving this. And it's bad luck that IAPP forms amyloid, and then the macrophage goes in and senses that improvement. So I really would bet here that this may be part of the pathogenesis of type 2 diabetes. So if I put my dominoes for type 2 diabetes, we have IAPP here activating NALM3, and that would drive IL-1. And now finally we get insulin resistance and beta cell death in type 2 diabetes. So again, basically it's about filling in these dominoes, so it's what the whole purpose would be. And it's not just type 2 diabetes. All of these diseases have NALM3 involvement. In the case of osteoarthritis, it's oxyapatite crystals. Icolats is shown very nicely in atherosclerosis cholesterol crystals. Amyloid, big amyloid in Alzheimer's. AMD, it's Brussels, and motor neuron. All these diseases have an IL-1 role, and it's all NALM3 sensing these noxious substances driving the disease forward. And then finally, and this is brand new stuff, I think, and I'm going to speculate for you now. So, people often ask me, how were you so lucky to get on the toll bandwagon? And I was all luck. I think Jules has acknowledged this himself in many ways, that let's say the toll protein didn't have a terdomain, it could have had a dectomain or something. And I was lucky to be in the IL-1 area, and people ask me what's the next frontier. I said, how the hell do I know? I was lucky the previous time, but I think the new frontier might be metabolism. And we got into this because of our diabetes study, and altered metabolism as a key inflammatory signal. And let me tell you why. It's been known probably for 50 years now. You put LPS on a macrophage, what happens? The medium goes yellow. Look at that. And that there's lactate. So the cell starts to pump out lactate, and 2-deoxyglucose is a way to block glycolysis, and it reverses this effect. So LPS causes a profound metabolic shift in macrophages. And this is all TOL4 dependent, by the way, and MyD88 dependent. You don't need to spend millions on fancy biomarkers or nanostring technologies. Just measure the colour of the medium is all you need to do if you work on TOL4. And we have found that this is a really important signal. And for example, 2-deoxyglucose, which blocks glycolysis, this is the Warburg effect, by the way. 2-DG blocks glycolysis, stops the lactate, right? Guess what 2-DG does? Profoundly blocks IL-1 production and doesn't affect TNF. There's a specific signal coming off glycolysis in response to TOL4. This is message, which requires glycolysis to drive the message. And even more, we found this profound increase in glycolysis and a very strange result, a profound increase in succinate. So the mitochondrial metabolism is altered, succinate levels rise, and here's some data. These are 3 humans now treated with LPS, and we measure succinate in their macrophage, a big boost in succinate levels. And that's a really interesting thing that stood out. And to summarise it for you, without giving you all the data, this could be a key danger signal. So we're moving now into metabolism, and how these innate receptors alter metabolic profiles, not because of ATP production, you might imagine, or biosynthesis, the signals coming off these metabolic intermediates. And in our case, we think succinate is a key signal, comes out of the mitochondria and drives IL-1, and the target's probably HIF, this hypoxia factor, because it will block these hydroxylases, and we've got loads of evidence for this, and it's a new signal. And of course, this is reminiscent of apoptosis. Who would have thought cytochrome C, a normal component of mitochondrial metabolism, turns out to be the signal to drive apoptosis through the caspases. So I think this could be a new frontier, basically, this altered metabolism in response to inflammation. Succinate could be a key damp, then, a danger signal, we think. And that, I think, is going to be an interesting future for this area, is to study these metabolic profiles now, in the context of host defense and inflammation. And I'll bet the same thing's happening in plants, because I'm sure the plant people will know there's many metabolic changes happening in plants. And maybe this metabolic flux, actually, is the first signal of host defense. A bacteria will alter metabolism. It'll soak up sugars, it'll release them, it'll change via TOLs, the intracellular metabolism, and that could be the first kick for a disturbance in homeostasis ultimately. And I'll finish with this sort of summary slide for you, which will sort of hopefully tie it all together. And again, this slide would not have been possible without the discoveries of Jules and Bruce going back. And all my work depended on their papers, and many of us, and I think Murray mentioned all the thousands of papers, which depended on these initial papers by Jules and Bruce, and I'm very grateful to them for that reason, as all of us should be, because this sort of scenario, who would have thought we'd get this idea, and this would be like a model of disease pathogenesis. So let's imagine this is rheumatoid arthritis for a minute. They're probably all caused by infections, I'd say that. And you get the PAX and the antigen. And here we have the primacy of TOLs and inflammasomes. We're sensing that and driving all your favourite signals. And I've just mentioned this metabolic flux might change here in some way, and HIF might be part of this. And now we've got our cytokines, and they drive inflammation. Now, very importantly, the inflammation is damaging to tissue. It's supposed to be, because it remodels. And the tissue injury generates NAMs, these endogenous types, with autoantigens now got released. And guess what? The same receptor system is now being kicked off. You get this vicious cycle. And then equally, the T and B cells are activated. They make more cytokines, of course, like IL-17. Autoantibodies come out, and they cause further inflammation. So this cycle here is adaptive immunity, provoking the inflammatory response even more. Now, we know this is probably true because of the drugs we have. So we know all the anti-cytokine therapies are working in rheumatoid to some extent and so on. So targeting cytokines is good. We know that in the case of abatacept stops T cell co-stimulation, rituximab affects B cells. Small molecule like anti-JAK, anti-SIC, and anti-P38, they all work. So if you stick a spanner, as we call it in Ireland, what's it called here, a wrench, into a machine, it'll go down, But this allows us now to come up with a reasonable model. Now, why would I get rheumatoid and you not? This happens during infection, remember, and it's self-limiting. And of course, the answer is genetic variation. There must be genetic variants that tip the point into chronicity. And its unrelenting cycling of these pathways give rise to disease and define those genes, and Bruce very eloquently told us about IBD. It's got to be a genetic background combined with an infectious insult of some kind that gives rise to all these diseases, and we need to map what that background might be. And of course, very nicely, and this is my last slide, I was asked to write a foreword for a book's about to come out called Nucleic Acid Sensors. And I asked him to write a foreword for this book, and Bruce wrote a chapter in this book, and I can't believe he's still writing reviews on TOLs. Where do you get the patience for that? I normally follow all my graduate students, but he orders it. And then I'm going to quote him. He writes here, look, if highly specific drugs capable of blocking or activating TLRs can be designed, it might be possible to treat certain diseases with unprecedented specificity. And that's the hope. Now that we have these receptors in our sites, surely targeting them will be useful, and we'll come up with a much better way to treat these awful inflammatory diseases, which are still unmanageable, like MS, motor neuron disease, Parkinson's, Alzheimer's. You know, rheumatoid is managed to some extent, but still there's a big need there as well. All these diseases then, hopefully, will yield, if Bruce's opinion, and many of us feel this is the case, will come true. And I'll finish on an optimistic note, and let's hope it does turn into therapies for people. And thank the people in the lab. Seth Masters did the work on my APP. This is my boat here on the River Liffey, what have you know. And Gillian, there's all my lab, isn't it great? This is a typical lab meeting. Gillian did all the work on the metabolism, and our very important collaborators, Steve Kahn gave us the transgenic mice for IPP. All the heart data, very importantly, was by Fatty Arslan and Gerald Pasterkamp. The kidney data was done by Steve Sachs for us in King's. And then all the metabolome, I spoke briefly, Isle Gottlieb and Ramnik Xavier helped all that. And very importantly, funding was from Science Foundation Ireland. And a big thank you to Martina, to be honest, because Ireland never used to invest in research. We used to emigrate our best people everywhere. Not just because of the potato famine, there was a famine in funding as well. And then Martina was one of the key engines to get the government to, as we say, cop onto themselves. And Science Foundation Ireland was founded about 10 years ago, and that's been a great help to us. And it's a great big thanks to Martina for helping to promote that. But let me finish with one last thing. You thought you were going to get away light. I wanted to say something special here, because it's a very special day for me, I have to say. Murray's invitation came in, it was last July, and I said yes immediately, because I figured what a great idea to meet Pam and talk about the plant stuff, because it's always fascinating me. And then it's always great to hear Jules and Bruce speak as well. And then lo and behold, the buggers win the Nobel Prize, which is very handy, isn't it, you know? But, you know, especially the younger people here, young scientists, you might wonder, why the hell am I in this business in the first place? You know, it's a tough game, research, it breaks your heart, things don't work, you know, you go home every night and you're wondering, why am I living at all in this world, you know? And we've all felt that way. And this is the reason why, right? And this is a very famous ad. So have you ever heard of Ernest Shackleton? He was an Irishman, I'll have you know, which most people don't realise. Ernest was Irish. He went to the Antarctic, and in 1913, he puts an ad in the London Times to recruit people for his fateful mission when he gets stuck in the ice. Remember, the ships get stuck in. And it's very famous because he gets everybody home safely. And this is the ad that should never have worked. It goes down in the history of marketing. If you do a marketing degree, they'll use this to teach you this ad shouldn't have worked. And yet it triggered like 8,000 responses, including, he said, 3 sporty women. He said, the rest were men. And this was the ad, look at this. Men wanted for hazardous journey, look at this. Small wages, bitter cold, long months of complete darkness, constant danger, just like doing a postdoc with Bruce Boyle. Safe return doubtful, but look, honour and recognition in case of success. And of course that's why we do it. And I'd like to honour our 2 Nobel laureates tonight yet again and recognise them for their fantastic and such important contribution to this field of immunology. And thank you all for listening.
Now you see why we got moved here. Yeah. Right. Just in passing, my son, the veterinarian, uses IL-1 receptor inhibitor every day as the most common drug in treatment of forced arthritis. There's never been a better example of the improvement in equine treatment than that inhibitor. Yeah. So it's very successful in horses.
It's incredible, isn't it? It's using horses. Yes, great.
Well, anybody want to make a comment then? We're right. You know, Luke, you already did put on this wonderful show and story. and you're right. I mean, I've got a lot of your genes, and I think, and I got to hold that.
Are you Irish, Mark?
Yeah, Irish.
Well, you will be tonight.
Yeah. But I mean, there'll never be another meeting like this, and I think it's absolutely a unique event. It's been a wonderful time. It couldn't have been better. For me, it's a dream come true. And we'll never forget it. And we thank you all so much for coming and taking part of this. It's really been a spectacular occasion. So, Jules, Bruce, and Pam, and Luke, and all the rest of you, thanks very much for making it possible.
Somehow, possibly, and turned on the gene for COX. And I got this from my PhD thesis. I gave this talk about 3 months ago about my PhD, and I had to use, remember we used to use these diazo group slides, Bruce? I had to turn one of those into a PowerPoint. And that was our knowledge of IL-1 signaling. And I was relentless. I wanted to know, how does IL-1 work? Can we understand this powerful cytokine, which is prodigiously pro-inflammatory? And then my next move was to go to Cambridge in the UK, and this, Murray, was my scientific father, actually. He was my postdoc mentor, Jerry Saklavada. He had discovered, in many ways, that IL-1 and TNF are key for arthritis. He was one of the key pioneers. And secondly, he was characterizing the receptor. And I figured I'd go to his lab, because if we can study the receptor, we might know how the thing works. And in the 90s, of course, this was our model for rheumatoid arthritis, dominoes, and the final domino falls over your rheumatoid arthritis. IL-1 and TNF were here, and they were driving this process, and of course that gave rise to drugs to block these cytokines. And anti-TNF came along as a key way to treat arthritis, because, in other words, TNF was proven to be a key domino, and that's earned billions for drug companies. I'm sure Bruce is amazed by that fact as well, having discovered TNF. And that's still the mainstay now for rheumatoid. But of course, the question was what drives it. I'll come back to that in a minute. But my question was, how does IL-1 work? How does it knock over these dominoes? And we just look at the receptor. I was an undergraduate at Trinity College Dublin, and in fact I was in the same year as Martina. Where's Martina? She's here somewhere. And a big thank you to Martina, by the way, because she also invited me to come to this talk tomorrow by a strange coincidence. And Martina did genetics, and I did biochemistry. We never met, strangely, back then. But as part of our degree program, we do a final year research dissertation. And I did biochemistry. And in the department of biochemistry in Trinity, it was mainly enzymology, and I hated enzymes with a passion, which is very strange to do a biochemistry degree. And you could pick a project from a list. And one project stood out for me, and it was called Prostaglandins in Crohn's disease. And that got my attention because I said, what are these prostaglandins? And as you all know, I hope they're these lipids that cause inflammation. And Bruce told us about Crohn's, still a big problem. I did that project in 1985, and it began my interest in inflammation. And prostaglandins were really hot at that time. They were the tolls of their day. There was incandescence around them. Everybody worked on prostaglandins. They were driving inflammation in all these diseases. So for my PhD, I went to London. I went to this place. This is one of the meccas of prostaglandin research. The Royal College of Surgeons in London. And in that department in pharmacology, a guy called John Vane had won the Nobel Prize. He was my first Nobel Prize person I met back then. And he discovered how aspirin works. And I went there to study prostaglandins because aspirin works by blocking prostaglandins. And a little anecdote for all you young students. There's me there. Before the ravages of age took over. That's 1985. Look at rheumatoid arthritis, even then I was working on that. And I was there about 3 months as a postgrad. I couldn't speak English then. The Irish could only speak the Irish language, as you know. The English had tried to destroy it, but we had survived. And I was there about 3 months, and Vane came to give a seminar. And he arrived, he was in the car park, and we all saw him come in, and he came up and he gave this seminar. And about halfway through, I spotted an inconsistency in his talk. He said something that didn't quite gel for me. And at the end of his talk, the chairman went, any questions? And would you believe a timid first-year graduate student that rose my hand tentatively? I was saying at lunch, actually, how many years training does it take to get someone to ask a question at a seminar? Probably 8 years. Yeah, most people are too frightened. But I put my hand up and I asked him this question, and he said, that's a very good question, I don't know the answer. He said, come up and see me afterwards. And I went up afterwards, and we had a chat, and he said, great question, I'll write to you, there was the days for email, and he sent me a letter with the answer. That single conversation, let this be a warning to our current two Nobelists, convinced me science was the business for me. That a paddy off the boat from Ireland, who could hardly speak English, that IL-1 was inducing cyclooxygenase. Now this was all done indirectly, we didn't clone the gene, but it was evidence that the COX enzyme was somehow being induced by IL-1, and I got a Fed's letter paper out of that, and this turned out to be correct, amazingly. And other people then went on to clone the gene, and the people who are pharmacologists will know there are two types of COXes, good COX and bad COX. The good COX is in your stomach and protects you, the prostaglandins are cytoprotective. The bad one's inflammatory and causes all this inflammation through prostaglandins. And why this was important was aspirin blocks both, and so does ibuprofen. And of course that's why it causes ulcers, because it stops the good COX and the bad COX. This led to the industry developing COX-2 specific inhibitors, and Celebrex and Vioxx came along, and they were much better now because they spared the stomach and there were no ulcers, but they were anti-inflammatory. Of course, troublingly, they got withdrawn, and that was another Irishman, Gareth Fitzgerald, spotted that Vioxx in particular had problems in the heart, it causes heart attacks, and they get withdrawn. But when they were launched, they were huge drug deals because they replaced all the other anti-inflammatory agents. And my project was part of this because we showed induction of this special COX, which became known as COX-2. And then I wondered how this pathway would work, and in 1988, This was our version of IL-1 signaling. We thought the receptor, which hadn't been really cloned then, went into the nucleus, challenge an Nobel laureate, and catch him out almost. And he was, and it's a good question. I said, this is the meritocracy. It really kind of energized me in that situation. That was great. And he was a big influence as a result, and there he is. And again, he won the Nobel Prize, as I say, for showing that aspirin works and similar anti-inflammatories. Aspirin works by blocking prostaglandins, and he showed prostaglandins were the key programming factors. Now, he had published a paper in Nature. He won the Nobel Prize on that single paper in 1971, inhibition of prostaglandin synthesis as a mechanism of action for aspirin, because it was a big unknown area. Now, my PhD project was all about prostaglandins, and at that time, this was the pathway for prostaglandins. There was arachidonic acid that was made, and you get an enzyme called cyclooxygenase that makes PGE2. Aspirin worked by blocking that enzyme, and that not much was known about the control of that pathway. Calcium was known to be an important signal, but two brand new fangled mediators of inflammation had been found in the mid-80s, and Bruce discovered one of them. One was called TNF, the other IL-1. These are cytokines made by macrophages during inflammation, and they were known to be very powerful inducers of prostaglandins. And my project was figure out how they work. How would IL-1 increase prostaglandins? And my very first project was IL-1, very powerful. What's its mechanism? These newfangled things called cytokines. And I published a paper in 1987 in Feb's Letters showing